Hello from my side. My name is Pandremenos. I'm coming from the laboratory from Manufacturing Systems and Automation of the University of Patras in Greece. The topic I'm going to present you today deals with simulation in rapid manufactured products. This is an outline of my presentation. I will begin with some definitions about simulation and mechanical models. I will then discuss about simulation in rapid manufactured products, and I will end with a case study of the custom project. So a definition that it is often used for simulation is that it is a process of designing a model of a real system and conducting experiments with this model for the purpose either to understand the behavior of the system or to evaluate various strategies for the operation of the system. In this scheme, you may see how mechanics works. Actually, a mechanical model is used to prevent events in reality, to predict events in reality. And it is built on three pillars: the environmental variables, the material variables, and some geometry variables. Finally, we must say that in order to create these models, these mechanical models, we should make a number of assumptions, both from the model to reality and backwards from the reality to the model. Let's now talk about why rapid manufacturing, why simulation is important in rapid manufactured products. The reasons are mainly two. The first one is that the rapid manufactured products present anisotropic behavior. This means that the material in the plane where the layers are manufactured are often stronger than in the perpendicular vertical direction where the material is weaker. Another reason is that the rapid manufactured products are characterized by a high degree of customization. This means that each product has unique geometrical and structural characteristics. So the standard procedures that are followed for the verification and the certification of the mass-produced products are not economically feasible to be utilized in rapid manufactured ones. Maybe a more familiar example to you is the buildings. Each building is most of the times unique, so we cannot create it in order to test it and then produce the correct building. So, for these two reasons, computer-aided verification is required. Within the custom project, several approaches for computer-aided verification have been developed. The first one is called testing approach. In this approach, the final design of the new product is verified and tested prior to its production in order to filter and ensure that only the acceptable products are produced. The second approach in the second approach, the challenge or bandwidth, or as it's called, the challenge defines the range in which certain loading cases of the new product should be. This means that the advantage of this approach is that it is not required for every single loading condition to check whether the product is correct, as we just check if the product is within some boundaries that we have defined, and this is sufficient. The third approach, the iterative, is an automated product design process where the verification results are fed back into the design system so as to improve the design. An advantage of this approach is that it produces and generates only certified products. The final approach, the analytical one, uses analytical relations between loading situation, material, and product geometry in order to make the verification. These systems, again, only produces acceptable copies. In order to define which computer-aided verification approach is suitable for the product we have, we should first look in the mechanical complexity of the product. Three types of complexity are defined: the environmental, the material, and the geometric complexity. Here you may see some typical examples of mechanical complexity. You may see in the three axes the three types of complexity and some typical products. And here you may see which are the preferred CAV approaches with respect to the mechanical complexity. However, the designer should always have to select the correct approach by full awareness. There is no a definite guide, a definite rule for this approach. Let's go now to the case study. The objective, the case study deals with helmets. And the objective is to customize and manufacture with rapid manufacturing the inner liner of the helmet. This will hopefully improve comfort and safety. The inner liner is the blue part. You can see in the figures. And here are some figures of the conventional in the left and the customized helmet inner liner in the right figure. So the objective for the verification of this customized product is to determine if the helmet with the custom comfort liner would indeed be safer than standard helmet. In general, all helmets have to pass a couple of physical safety tests before being introduced in the market. However, as this helmet is customized now, we cannot do all this, we cannot make physical tests in an economical, feasible way for the helmets. And thus, virtual testing is required. For the verification, the analytical method has been utilized as we had the low material complexity, as only linear material models were used. The geometric complexity is also low, as only the thickness of the comfort liner is sufficient to define the geometry. And finally, the environmental complexity, we may consider that it is high, as complex load cases of both impact absorption and tensor tests are needed. These are the tests that the comfort liner will have its influence. The first one is the impact absorption test, where the peak acceleration must be less than 275 Gs. The head injury criteria should be less than 2,400. Head injury criteria is an empirical function that evaluates the expected severity of the human brain injury induced by an impact. And finally, we have the retention or detachment test, as it is named, where the helmet's rotation after the test must not exceed the 30 degrees. This is the FE model